All right, so what we're going to be talking about and thinking about today are the ways that forces combine on objects and how those forces, those combined forces, influence the motion of objects. So we talked a little bit about this the other day when I was mentioning that forces are vector quantities, and we're going to be doing some vector math to figure things out. And this is really the first step in thinking about that kind of vector mathematics. We're going to learn two things today, focus on two things. One is free body diagrams. And free body diagrams are just, there's rules to them, especially if you're in AP Physics, but really they're designed to be something that's useful for you. Free body diagrams allow you to think about all the forces acting on an object and the directions of those forces. That is the real key piece to a free body diagram. And then we're going to think about a special condition called equilibrium, and use that to try to figure out, okay, well, if we know an object is in this special condition called equilibrium, then can we use that information to determine an unknown force? So I'm going to walk you through all of this stuff. The brief reminder of what we did earlier in the week. We talked about forces as being pushes or pulls, but forces are, we kind of don't know exactly what they are. We know what they feel like, and we know what they do. Nobody really understands like how forces are communicated. We have lots of crazy theories, but it's not super easy. In this class, we're going to be measuring forces in newtons, and this came up, but a newton is not like a base unit. It's made up of other units, and it's just kind of a complicated thing, which is 1 kilogram times 1 meter divided by seconds squared. And we'll talk about what, like, we can kind of tease this apart, because basically what a newton tells us is that this is the amount of force that it would take to accelerate a 1 kilogram object at 1 meter per second squared. That's really what we're looking at. But we'll play around with units a little bit more down the road. In the non-metric system, we use pounds for force. And that can be really confusing. We'll hit this several times because we think of pounds as only being used to measure weight. And of course, weight is a force. Weight is the magnitude of the force of gravity acting on an object. But it gets confusing when we associate pounds only with weight, because then it gets weird. Because I can push on a car with a force of 17 pounds. That doesn't mean the car weighs 17 pounds. It doesn't mean that I weigh 17 pounds. That's the size of the pushing force that I'm exerting on the car. And so newtons is a little bit easier because we generally don't talk about weight in newtons. So it's a little bit easier for most people to think about newtons as being force. And then we talked about the idea, and this is where Newton's laws come in, which is that forces sometimes cause acceleration. And the way it works is that if you take all the forces on an object and combine them mathematically, which I haven't shown you how to do yet, then it turns out that they don't all just sort of cancel each other out. Then the object that is experiencing those forces will accelerate. If we take all the forces acting on an object and we combine them mathematically and what we get is nothing, when it's all said and done, there's no overall force on the object, then it won't accelerate. That's it. And it's simple to state, overall forces cause acceleration. That's it. But it's really hard to kind of tease out how and when that's happening, partially because our brain plays tricks on us. If we look at this diagram right here, we can, this is set up deliberately so that we can kind of like, we can sort of do some of the math automatically. Like when I look at this upward force and this downward force that are both 4,000 newtons, like it's pretty easy for me to recognize, oh, that those cancel out. Whereas this force to the left and this force to the right aren't the same. Overall, there's more force to the right. So in this diagram, we can kind of guess that this object will accelerate to the right, and that would be correct. When we talk about forces, it's going to be really important to be able to identify, because we're going to have lots of forces acting on objects. So one of the things that I'm going to push is real precise vocabulary when we're talking about forces, because otherwise, it's not that you're wrong, it's that it's really confusing. So one of the forces that we're going to talk about is weight. Weight is the force of gravity on an object, and we talked about how to find an object's weight, which is to multiply its mass by that g number. Weight is equal to an object's mass times g. G is not gravity. And you all are going to get yourselves into a lot of trouble because you're going to want to say mass times gravity. G is for gravity, but it's not. G is for acceleration. The acceleration of an object in free fall near the surface of the earth. That's what G is. It's not gravity. If you call this mass times gravity, I'm going to correct you. Mass times the acceleration of an object in free fall near the surface of the earth. The best way to say this is mass times G, because G is the acceleration of an object in free fall near the surface of the earth. If you say m times g or mass times g, you're good. If you say mass times gravity, you're wrong. Gravity is a force, g is an acceleration. And it's not your fault that the morons who gave this constant a letter chose the letter g instead of something that wouldn't have made everybody on the planet call it gravity. But that's what happened, and so we have to work with it. The reason that it's important for you to be real precise about this is because if you're not, what you're going to find is that you get confused between the acceleration caused by the Earth's gravity when an object is in free fall near the surface of the Earth, which is 9.8 meters per second squared, the force of gravity, which is a force that the Earth, that its gravitational field exerts on all objects near the surface of the Earth, and the magnitude of the gravitational force. You're going to get confused, you'll confuse yourself. And I say that based on experience. So be aware, g is not gravity, g is the acceleration of an object in free fall near the surface of the Earth. We're going to look at spring forces, and we'll look in detail at these later, but essentially the key with spring forces is that they are proportional to what's called the deflection of the spring. And the proportionality constant is called the spring constant. We usually use a K. The deflection of the spring, unfortunately, we often use X for that. And so sometimes we have two X's to think about. We're not going to deal with this right away, but just understand that when we talk about spring forces, we're talking about a force that changes. It's not constant. At any one time, the spring force can be different depending on how far it's stretched or squished. So that's going to be something that we need to kind of, we're going to need to be able to work with that. Tension is the pulling force in both directions along a rope or a string or chain. And we did talk about this just the tiniest bit, but the thing about tension that's weird is, first of all, you can't push. So if I have something connected to something else via a string, I cannot push. So I can't if I have this giga and I want to make it go to your right, I can't do it with this string. But I can pull it, I can make it go the other direction toward your left by pulling it on the string. That's weird. I mean, it's not weird, but it's a little bit unusual. It's really different, for example, from like a stick attached to something. If I take a stick and I attach it to this eraser, then I can pull the eraser or push the eraser. I can move the eraser whatever direction I want, because the meter stick is a rigid body, but a string or a cable isn't. It only exerts force along the string. And then the other weird thing is that tension is acting in both directions at all times on every point along that string. So or rope or chain or whatever, and so we've got, it's this weird thing where it's like, what direction is tension? And the answer is both directions. If I look at a single point on this rope, it is being pulled in both directions at the same time. And the force acting on that point is whatever the tension is in both directions. If we look at one end of the string, it's being pulled with an amount of tension equal to the tension in the string. And if we look at another, like the other side, it's being pulled in the opposite direction. So it's this weird transmission of a pulling force. And so we'll be working with that a lot. The normal force is the most complicated one. This one is a force from a surface that pushes perpendicular. Which is a word, perpendicularly. And the thing about the normal force is this word normal also means perpendicular. If you remember geometry, you probably learned that at some point in geometry or maybe trigonometry. And this is another one of those things, it's not your fault, it's like G. Everybody wants G to be gravity, but it's not. It's the acceleration of an object in free fall near the surface of the earth. And everybody wants normal force to mean the usual force or the typical force. In fact, I will bet, so I don't have any money. You all know this. You didn't need me to tell you that I have no money. But I do have a credit card. And I will bet the entire balance, I'm not actually kidding at all, I will bet the entire balance of this credit card, not the money that I've already spent, but like, I will give you a blank check for my entire credit limit if nobody in either of my physics classes this year accidentally calls the normal force the natural force. Because it happens every single year. Somebody calls it the natural force. Because this word normal means like usual or typical or natural. And that's just like, it makes perfect sense, except that's not what this word means at all. This means perpendicular. Surfaces push back. They push back on things that are pushing on them. If I push on the board, it pushes back on me. The direction of the pushing back force is at a 90-degree angle to the surface of the board. The floor is pushing back on me right now. And it's pushing back at a 90-degree angle to the surface of the floor. There is a force from this ramp onto this cart. That force is at a 90-degree angle to the surface of the ramp. If we have a curved surface and there's something resting on that surface, like right here, then the normal force is perpendicular to the point at which that object is resting. That's what the normal force is. Sometimes we call those surface forces. Okay, and then the last force is friction. Friction is super complicated because friction is this magic slowing down force. So it's a magic slower downer. But the rules of friction are super complicated. It changes. And not only does it change like magnitude, but the rules of how it changes aren't always the same. So if we want to know something about friction, if we want to figure out something about how friction is slowing an object down, then we have to know a whole bunch of things about that object in order to figure that out. So friction is the most complicated one. The nice thing about friction, though, is that if we establish a situation, then we can say, okay, in this situation, what's friction? That's a relatively easy thing to do, okay? So these are just some of the common forces. And then a lot of times we'll talk about forces, we'll just be like, oh, well, now there's a person pushing on like a cart, or there's a moose is pulling out a garbage can with its teeth. Those are other forces that might be present in a scenario, but they're not like, they don't have an official name. Like there's not a moose force that you're gonna find listed in textbooks. But these forces you'll hear about. You'll hear people talking about weight and tension and the normal force and things like that. And so we need to be able to get used to this terminology. And then these variables here, W for weight, F, S, P, T, N, F, like those are common abbreviations for those forces, but they're not the only ones. For weight, a lot of times people will just use mg, because that's weight. A lot of times people will use F with a little g, the force of gravity on an object. That's true as well. A lot of times people will refer to, well, I think those are the two most common. There's probably other ways that people refer to it as well. Tension, I will interchangeably write F with a little t by it. The normal force, the same thing, Fn. Friction, F with a little f. Capital F generally means force, so there's lots of different ways that you'll see these referred to. And again, like that's not my idea, unfortunately. This is just really common. So, so we have to be flexible with that stuff. When it comes to drawing these pictures that I call free body diagrams, basically what free body diagrams do is for any object, they show all the forces acting on the object. And they show the forces as arrows, and there's a couple rules. One is, if we know something about the size or the relative size of a force, we try to use that arrow, the length of that arrow to indicate that. So like in this diagram right here, it looks like this force, the normal force, the weight, this says F boy, so this is like a boy pulling on something or pushing on something. And those look like they're all about the same size. And then this force over here, which is F with a little f, that's the friction force, that's smaller. We can guess that from the diagram. When you're making diagrams, you do the best you can to communicate the information you know, but you won't always know all of it. And then we always draw these arrows pointing away from the object. And in AP physics, that's super important. In the regular physics class, it's less important. If you draw an arrow toward an object because it's a pushing force, I'm fine with that. The AP trolls will not be fine. So the AP trolls, you've got to draw it as an arrow pointing away. We label the forces, and you can use those symbols that I just showed you, W and mg and F with a subscript. The AP trolls aren't super picky about that as long as you use something that's like been used by somebody else in the past. Like you can use mg for weight or W for weight or F with a little g for weight, but you can't use FQ because in your mind Q is the name of your friend Quentin and you always think about Quentin's weight. You know what I mean? Like you can't just make up your own terminology for it. I will always draw objects as rectangles because that way, if it's on a tilted surface, it's really easy to see that, which is really often handy. AP trolls like to use a dot. Why do they use a dot? Because they're trolls. They use a dot because it's worse, and they like that. They like making your life more difficult. And then often, we're going to include some sort of a reference coordinate system, not because your forces can or will always line up with that, like they do in this example, but because typically what that's going to allow somebody to do is look at your free body diagram and know at a glance whether or not there are forces that will need to be described as two components in order to align with this system. Okay, so and we'll get into that down the road. We won't have to worry about that at all today. You'll see a couple of examples that hint at, well, you'll see one example that sort of hints at why that might be the case. And then, so let's draw some pictures. I'm going to just do this really quickly. These are probably going to be somewhat obvious to you, but if we have a chair at rest on the ground, this is going to be our chair. Always going to draw it as a single rectangle, and on Earth, there's always the force of gravity, so I'll call that mg, m times g, not m times gravity, m times g. And if we have a chair at rest, and so one of the things that we talked about is the idea that things can be instantaneously motionless. Like if you throw a ball up in the air, the top of its motion, it's like instantaneously, it has a velocity of 0 for an amount of time that has no length whatsoever, and then it starts moving down. And when we talk about objects at rest, we generally are implying for more than an instant. Okay, so in this case, a chair at rest on the ground doesn't mean that we looked at it and at a single timeless instant it was at rest and then it started moving. What we mean is it's not moving for some period of time. We're observing it, okay? So what does that tell us? That tells us that it can't be accelerating. Motionless things aren't accelerating. And that tells us that all the forces have to be balanced. That tells us that there's got to be another force the same size as the chair's weight in the other direction. And that force is going to come from the ground. That's a surface force. That's a normal force. So the normal force of the ground is pushing up with the exact same magnitude of force as the Earth's gravitational field is pulling down, right? So that's a chair at rest on the ground. Here's another example. Let's say we've got a physics geegaw like this, and now let's say that we're moving, but we're moving at a constant velocity. What are the forces acting on it? Well, there's a downward force from gravity. So here's my geegaw. It's being pulled down. The magnitude of that force is the mass of this geegaw times g, which is the acceleration of an object in free fall near the surface of the Earth. And then there's an upward force. It's not resting on a surface. There's no normal force here, but there's tension in this string. So tension is pulling it up. These two forces are balanced. We know they're balanced because it's moving at a constant velocity. There's no acceleration. So that must mean that all the forces on the geegaw, when we add them all together, come up to 0. And intuitively we can see that these two forces are in opposite directions. So they have to be the same size in order for the overall force to be 0 on this geegaw. And some of you are like, well, wait a second, what about the force that's pushing it this way? And the answer is, Newton's first law says that objects that are moving do not require a force in order to keep moving. Newton's first law says objects in motion will stay in motion unless there's an overall force acting upon them. So right now, this is motionless. To get it to move, I have to exert a force. But once it's moving, I no longer need to exert a force. It's already moving. So there's this, like when are we looking at it? Like, are we looking at it during the transition from motionlessness to constant velocity? Because if that's the case, then we do need a force to accelerate it. But once it's moving at a constant velocity, we no longer need a force. You can see the force, the acceleration force. You can see where that force is coming from. Remember, strings can't push. So I have to pull this with the string to get it to move. If I go from not moving to moving, did you see that? It tilted just a little bit. Just watch the string. You'll see it angle. You see that? You'll see it even more if I accelerate it quickly. Watch. Did you see that? Like, this is on the video. Here. Video land. You'll see that. Right? Play it back. You'll see. There's a moment during which the string is angled like this. It's pulling the geegaw this way. And then the geegaw starts swinging like a pendulum, right? And then eventually it stops, and then we just have like I'm just sort of taking my geegaw for a walk, but I'm not pushing it along. It's moving on its own. What if it's a balloon? Well, if it's a balloon, it should just sort of be the same thing, right? Yeah, we have balloons under our sinks. So here's what it should look like, right? It should just look like this. Same exact situation, except look what happens when I walk with the balloon. Now my string is angled the whole time, not just when I start moving. And it's always angled in the opposite direction of the way that I'm moving. So what does that mean? Well, it means that if I'm going to draw my free body diagram for the balloon, I have to draw my string at an angle. Strings are always pulling in the direction of the string. The balloon still has weight, it's still being pulled down by the Earth's gravitational field, so these are my forces now, but we have a problem. And that problem, you guys have the math to do this, we haven't talked about it yet, so some of you might see this and some of you might not, but that problem is that actually, like, kind of think about this tension force as sort of having a right and an up part to it. This part of the tension force and the weight of the balloon look like they've got to be canceling out, right? That sort of makes sense to us, because it's not changing elevation above the ground. But this part doesn't appear to be balanced out by anything. And that's a problem, because if this isn't balanced out by anything, then Newton's second law says it should be accelerating. That's what we figured out, is that overall forces lead to acceleration. This force looks like it's kind of like it's a leftover. So, but when I was walking with the balloon, I was moving at pretty much a constant velocity. So how do we solve that problem? The answer is, there's another force. There's gotta be. There's another force acting on the balloon, yeah. It's not friction per se, but I think you know what it is. You're thinking friction from the air, right? And we call friction from the air, and then the fact that, like, the air has to get moved out of the way, we take that and we combine it into something called air resistance. So you're right, you're not wrong, it's just, we call it air resistance. So in that case, there would be a third force, the force from the air. And there is some friction from the air kind of on the sides of the balloon, but there's also something different. When you try to push through something, it's not friction, because you're pushing straight on, you're not sliding along it, and we just call those resistance forces. So air resistance, or like fluids resist motion, like water. So that was actually happening here too, with the gewgaw. We just couldn't see it because the force of air on the gewgaw was pretty small. But it turns out, interestingly, that the faster you go, the more air resistance there is. So if I run with the gewgaw, you can see it's angled just a little bit, right? I'm just going to feedback now. You can sort of see it angling just a little bit, but that's only because I'm so swift. If I was weak and slow, like most of you, you would never see that. There's a lot of disbelief. They're looking at me as if they don't believe what I just said. You know it's true. All right, so last couple of things that I want to talk about are going to relate these free body diagram to Newton's second law, and then we're going to look at a special condition called equilibrium that's going to make our lives easier to start with. So remember, we talked about this the other day. What Newton's second law says is that if we apply an overall force to an object, it will accelerate. It will accelerate more if there's a larger overall force, but as that object's mass increases, it will accelerate less. So this is backwards. Smaller masses will not have less acceleration. Smaller masses will have larger acceleration. Sorry. So more overall force leads to more acceleration. Smaller mass leads to more acceleration. And if there is no overall force at all, then there's no acceleration. No acceleration doesn't mean it's motionless. It means it's either motionless or moving at a constant velocity. And this right here is Newton's second law mathematically. This sigma means sum of. F means all the forces on an object. Equals is, I think you know. M means mass, A means acceleration. If we add up mathematically all the forces on an object, that will be equal to that object's mass times its acceleration, provided we use the right units, which we'll talk about later. So one thing to, like, cautionary note is that we tend to think about Newton's second law as being F equals ma. F equals ma, F equals ma. That's not Newton's second law. Newton's second law says the sum of forces, sigma F equals ma. One force does not necessarily cause acceleration. I can push on the whiteboard. and I'm exerting a force on it. I'm exerting a rather large force. I'm a small, weak man, but if I were to push that hard on any one of you, and you weren't expecting it, you would move. Like, you could resist me if you knew, right? Like, you could brace yourself, but if you were just standing in the hallway and I came up and I pushed this hard on you, you would move, you might even fall over because you just weren't expecting it. But the whiteboard doesn't go anywhere. I'm pushing with a large force, it doesn't move. Why? Because my force isn't the only one. There's other forces on the whiteboard. There's forces from the wall behind it. And that is a force that can change, and the size of my force determines the size of the force with which the wall pushes on the whiteboard. The harder I push, the harder the wall pushes back. I can't push hard enough to make this whiteboard move, no matter what I do. So one individual force is not the determining factor. It's all the forces added together. Okay? And then when we, so Newton's second law says the sum of the forces will equal an object's mass times its acceleration. But if there is no acceleration, then acceleration is zero, which means mass times acceleration is zero, which means the sum of the forces on an object will be zero, which means that all of those forces balance out and the object's motion won't change. That's where Newton's first law comes from. If there's no overall force on an object, then its acceleration will be zero. If its acceleration is zero, then it'll stay at rest if it's not moving, and it'll keep moving the same speed in the same direction if it's already moving. And we can use that along with some magic to try to figure out, like, well, what are some forces acting on an object? So for example, if we have an object that is in the air, that is suspended by 3 strings pulling in 3 different directions, if we measure the force and the direction of 2 of those strings, then we can determine what the overall force and direction of the 3rd string has to be in order to balance those first 2 out. And we use that kind of thing all the time in architecture. So if you've ever seen like cool like cantilevered buildings or canopies or stuff like that, all of that has to do with, well, we know what all these other forces need to be, and because of that, we can figure out how much force is going to be in the cable that connects the canopy to the building. Or we can figure out how much force is going to be in the supporting girder that's holding up this cantilevered part of the building. So that's some like architecture, physics, structural engineering stuff that's really common. The vocabulary here is unfortunate. I'm going to say this quickly, we'll come back to it. When we talk about objects that are not moving at all and stay not moving, we say that those objects are in equilibrium because all the forces are balanced. We say that it's static equilibrium because it's not moving. If we have something moving at a constant velocity, its acceleration is zero, it's still in equilibrium, but we say it's dynamic equilibrium because its position is changing. Unfortunately, we also use the term dynamics to talk about accelerated motion. Dynamic equilibrium means the forces are balanced, but the position is changing. Dynamics is the branch of physics that studies unbalanced forces and the resulting change in velocity. Dynamic just means changing. So dynamic equilibrium refers to constant velocity, changing position. Dynamics refers to unbalanced forces, changing velocity. And that's one of those many things that is really annoying. So as I mentioned before, we're going to try to use this stuff to think about unknown forces. And the specific unknown force that I want you all to think about today is a supercart with something in front of it. So you're going to take a supercart and you're going to put so the best thing are those little metal bars, and those, I don't know where those are, but we'll figure it out. And what we're going to try to do is figure out the overall friction acting on the supercart and the thing in front of it at the same time. So there's friction here, right? And you can see it, you can hear it, like the cart itself, not so much the block of wood, that's where all the friction is, right? We're using the block of wood in conjunction with the supercard because the supercard has a built-in force sensor. So if we attach something to the force sensor and pull on it, we can measure forces really easily. And it can measure speed and distance and acceleration as well. We're using the supercard just as a measuring tool, basically. Like this is just a really handy way of being able to make really accurate measurements of position, velocity, acceleration, and force. So you're gonna use a supercard with something in front of it, and that whole thing together is our object. This is our object, not just the supercard, not just the block that's in front of it. And then you're going to draw a free body diagram for the object as a whole. That's gonna look like this, right? This is our object. It's a rectangle, because all things are rectangles in physics, while it's on a horizontal track. And then I want you to think back to what we started with today. What we started with was me asking you to tell me how you could find acceleration in an object by using rulers and stopwatches. And now what I want you to do is I want you to tell me how could you find the force of friction acting on a supercard. We know it's on a horizontal track. We know it's got something in front of it. This is our scenario. How much friction is acting on the supercard right now? How can we figure that out? How can you figure it out, and how can you prove that what you're doing to figure it out makes sense, right? Because you could come up with a number, and that number might be wrong. So what I want you to do is, so we're gonna have a couple of days to do this. I actually want you to figure this out. Supercard, and let's just use, I think these blocks of wood are fine. Let's just use these blocks of wood. Use supercard with a block of wood. We wanna know how much friction is there. Ultimately, we're gonna use that to make some other predictions. And so in the short term, we wanna know how much friction is acting on it. In the long term, once we know the amount of friction that's acting upon it, we can use that to make all sorts of other predictions. Okay, does anybody have any questions before we get started? So this is super open-ended, and I mentioned that we're doing things like this is really different from what you've done before. Some of you have a great idea of how you're gonna do this, which is great. Some of you are like, you want me to do what now? And just recognize that we just jumped into the pool, but I'm not gonna let anybody thrash around, okay? I'm there, I got you covered, but I want you to see what it feels like to start with the rules and no roadmap to get to the answer. And then ultimately, we'll all work together to figure out how to get there. Okay, so you have the rest of the period to think about this and make some measurements. You can play around, you can talk. Don't work in groups of more than 2 or 3. Ideally 2, like work in pairs if you can. If there's not enough supercards, then fine, work in a group of 3, but no more than a group of 3 so that you're really actively engaged in what's going on. And you have the rest of the class to work on this.